As robotic manipulators move from structured factories into unstructured, everyday environments, they must interact safely through physical contact. This requires both compliance and accurate force control. Classical inverse dynamics controllers are reactive, but they tend to fall into local optima and can violate physical and safety limits. Model predictive control improves on this, yet QP-based methods linearize the dynamics and assume constant contact, leading to short horizons and low update rates, while DDP-based methods are sensitive to initialization and require differentiable costs. Sampling-based MPPI naturally handles nonlinear dynamics, but existing manipulation approaches stay at the kinematic level. Torque-level MPPI that explicitly solves the full rigid body dynamics has remained unexplored. We propose a real-time, dynamics-based torque sampling MPPI framework. To our knowledge, this is the first MPPI manipulation method that explicitly solves the full rigid body dynamics inside the optimization loop. By directly sampling joint torques with a custom GPU parallelized solver, our controller runs at over 166 Hz with a 0.18 second prediction horizon on a 7-degree of freedom Franca robot. This enables hybrid motion force control, inherent compliance, and feed-forward force regulation while satisfying safety constraints. At the core, each GPU thread runs a single rollout. We sample joint torques and solve the forward dynamics for the resulting joint acceleration. The stage is then integrated forward over the horizon, and the inertia matrix M and the bias term H are recomputed analytically at every time step to keep the prediction accurate. All robot parameters are stored in GPU constant memory, so thousands of rollouts can be propagated in parallel, in real time. Every rollout is scored with a running cost combining task and constraint terms. Crucially, the task cost adds a force objective on top of motion tracking, and this is what makes the controller force-aware, unlike conventional motion-only MPPI. The sampled trajectories are then merged through an importance-weighted average to form the optimal torque sequence, and the first command is applied to the robot at each control step. We verify the control performance of the proposed framework. Here we compare our method against a conventional acceleration sampling MPPI under end effector perturbation. While both regulate the desired pose, our torque level controller responds compliantly to the disturbance and recovers smoothly, whereas the conventional approach reacts stiffly, triggering an emergency stop. Applies force control along the x-axis while regulating position on the other axis. When the end effector is pushed, it yields compliantly in the direction of the applied force, then returns to the desired force and pose once the disturbance is removed. In the second scenario, we demonstrate hybrid motion force control while maintaining contact with the surface. The robot applies force control along the z-axis to stay in contact, position control along the negative y-axis to slide, and regulates the remaining axes. It maintains a consistent contact force across both flat and curved surfaces, adapting to the geometry without losing contact. Final scenario, we show dynamic obstacle avoidance during contact hitch motion. Control along the negative y-axis, a moving obstacle, a mustard container, is introduced into the workspace. The collision avoidance cost steers the manipulator away from the obstacle in real time, while still maintaining its force and motion objectives. Thank you for watching. For more details, please refer to our paper.